Hi again everyone, this is Hassan Termos, and this will be the final revision session organized by the CCS for EECE 330 this semester. And today we're going to be solving a few problems on graphs. I hope you find this beneficial. Now let's jump right in. So the first problem we're going to solve is problem 3 from the fall 2021 final previous exam. So we're given an n by n integer matrix representing a maze, and this is an example. The entry point of the maze is the top left corner, i.e. the cell with the value 10 in the example, and the exit point is the bottom right corner, i.e. the cell with the value 3 in the example. You are allowed to move horizontally, both left and right, and vertically, both up and down, but not diagonally. Part A. Further to the above, the numbers in the cells describe the height of a cell. You are only allowed to move from a cell to another with a smaller or equal height. E.g., in the example, you cannot move down from the cell with value 10 because the cell below has a higher value 12. Provide an algorithm that returns true if there is a way to exit the maze through legal moves and false otherwise. So we have this maze, and there are some legal moves we're allowed to do. Namely, we're allowed to move from a cell with a certain height to another adjacent cell with a lower or equal height. And we're asked to check if there is a path consisting of legal moves that can take us from this upper left corner to this lower right corner. So this is a straightforward graph problem. We're gonna model this maze as a graph as follows. So each node is gonna correspond to one cell in the graph. And let me just try this out. Okay. And we're gonna have edges between adjacent cells. We're gonna have directed edges between adjacent cells representing legal moves. So for example, I'm allowed to go from 10 to 7. So I'm gonna have an edge from 10 to 7, and this is going to be a directed edge. This graph is going to be a directed graph because I want to represent the fact that I'm allowed to go from 10 to 7, but I'm not allowed to go from 7 to 10. So the relationship isn't symmetric. So we want directed edges. So we can just fill this entire thing out. And as you can see here, we have edges going in both directions because we're allowed to go from either of these nodes to the other because they have the same value. So anyways, now the problem is translated from having to find a path in this maze to having to find a path in this graph. And the new problem basically is can we find a path from this node to this node? So this is the source node, and this is the destination node, and we want to see if there exists a path between them, and this can simply be done using DFS or BFS. So this basically solves problem A. Now on to problem B. Suppose now we drop the restriction from part A, i.e. we can go from a cell to any adjacent cell regardless of their values. However, there is a score associated with each move. A move from a cell with value x to a cell with value y affects the score as follows. If x is greater than or equal to y, the score increases by x minus y. E.g., a move from 10 to 7, score increases by 3. If x is less than y, the score decreases by 2 into y minus x. So we're adding minus 2 into y minus x to the score. E.g., a move from 10 to 12, score decreases by 2 times 2, which is 4. Provide an algorithm that finds the highest score possible to reach the exit. So now we're allowed to move from any node to any other adjacent node, but our moves have a certain weight to them. So there's a certain score, or rather a certain effect on the score that each move is gonna make. So we can represent this as like a similar setup where each node corresponds to a cell in the matrix. But now we're allowed to go from 10 to 7 and from 7 to 10. But we're still gonna use a directed graph because the move from 10 to 7 is not equivalent to the move from 7 to 10. They have different weights, so we want to have different edges to represent them. So we're gonna have all of these edges. They're all valid moves. And then we're gonna assign a weight to each of those moves. So if we move from 10 to 7, based on the description here, moving from 10 to 7 would have a weight of +3, so it's gonna increase the score by 3, while moving, for example, from 7 to 10 would have an effect of -6. And we can just fill this entire thing out. I've done this previously, so this is what we'll end up with. This is a graph where every edge has a weight, and the weight is the value that will be added to the score if we make that move. And now the problem is translated to the following. We want to find the path from this node to this node. So let's call this the source and call this the destination. And we want to find the path from the source to the destination that has the maximum sum of weights. Because by maximizing the sum of weights, we're going to be maximizing the score. Here, the score is equal to the sum of weights of the path, or we can call it the total cost of the path. So we're trying to maximize this total cost, and we're not really familiar with algorithms that are designed to maximize the total cost of a path, but we're familiar with algorithms that are designed to minimize the total cost of a path. So what we can do is we can just flip the signs of all of these edges. So we'd end up with a graph like this. As you can see, here the edge with weight 3, now it has a weight of -3. The edge with a weight of 6 now has a weight of, the edge with a weight of -6 now has a weight of 6. So all the weights are, so we changed the signs of all of the weights. And the reason we did this is now the score is not equal to the total cost. The score is actually now equal to the negative of the total cost. So there's this negative relationship between the total cost of the path and the score. And we're going to use that because now to maximize the score, we have to minimize the total cost. So this trick is useful for when you want to maximize the sum of weights on a path. You can just change the sign and minimize the sum of weights on the path, and you'd basically be solving the problem of maximizing the sum in the original graph. So now by finding the path with the minimum total cost in this graph, it's the same as finding the path with the maximum total cost in this graph, which is finding the path with the maximum score. And we know how to find the path with the minimum total cost in this graph. We just use Bellman-Ford. And we can verify that there are no negative weight cycles. The way I like to intuitively think about this, first of all, notice that in this graph, the weight of any edge, uv, is greater than or equal to the value of v minus the value of u. And we can verify this by taking cases. Now if we take any simple cycle, then the total cost of a simple cycle starting from u, and then going u1, u2, then un, and then back to u, the total cost of this entire loop is going to be the weight of u1 plus the weight of u1, u2 plus the weight of u2, u3 plus etc. the weight of un minus 1n. Let me just move this. Plus the weight of u and u. And this would be greater than or equal to u1 dot val minus u dot val plus u2 dot val minus u1 dot val plus u3 dot val minus u2 dot val, etc. plus let's say un dot val minus un minus 1 dot val plus u dot val minus un dot val, and these are just gonna cancel out. So u2 is gonna cancel with this u2, u1 is gonna cancel with this, u3 is gonna cancel with something here, this is gonna cancel with this is gonna cancel with something here, u dot val is gonna cancel with the one from the first term, and overall this is gonna be equal to 0. So the total cost of any simple cycle is gonna be greater than or equal to 0. So the key takeaway from this problem is sometimes you have to modify the way you define a graph. So you might have to go with a definition other than the one that first occurs to you, so that you can apply an algorithm that you already know. Now the second problem we're gonna solve is gonna be problem 2 from the fall 2022 EECE 330 final. We're given a directed graph G, and we say a node C is a central node if for all nodes V in G there exists a path from C to V, i.e. all nodes are reachable from C. Our aim is to find such a central node C if it exists. In this figure, or actually in this graph, node 0 is central, so are nodes 1 and 3. Node 2 is not central because there is no path from 2 to 0, for instance. So let's verify the claim that the node 0 is central. So we're told that a central node is defined as a node that has a path to all other nodes. So 0 can reach 4, it can reach 2, it can reach 1, it can reach 3, and obviously it can reach itself. So this is the definition of a central node. And it might be a good idea if you're faced with such a problem to play around with the definition just to get a feel to what it's like. Now for part A, suppose node U is not central, and say node V is reachable from U, i.e. there exists a path from U to V. Can we say whether or not V is central? Justify your answer. So we have this node U, and there are some outgoing edges from it, and at some point it can reach a node V. So V is reachable from U. And we know U is not central. So can we tell if V is central? So let's think about this. Let's say V was central. So let's assume V is central. And we know that U can reach V. So if V is central, then U should be able to reach all other nodes by just following the path to V, and then from V it can go to any other node, because we're assuming V is central, so it can reach all other nodes. But we know U is not central. So by contradiction, we know that V cannot be central. So yeah, in such a case, if U is not central and V is reachable from U, then we know for a fact that V is not central. Okay, for part B, we're asked to provide an algorithm in pseudocode named isCentral of GU, which given a directed graph G and a node U returns true if U is central in G and returns false otherwise. Hint, use DFS. Okay, so we're given a graph. Okay, so we're given a graph, some directed graph, and we're given a node U in that graph. So let's say this is U, and we're asked to check if U is central. So we have this function we're gonna have to define, isCentral of GU. And this is kind of straightforward, because from the definition we know that if U is central, then all nodes are reachable from U. right? That's what it means for the node to be central. So we can just DFS, we can just apply DFS on G starting from U. And then we check the visited array. So recall that the visited array would have an entry of true corresponding to every node that was visited during the process of the DFS, and it's going to be false for every node that wasn't visited. So we're going to check the visited array. If all entries are true, that means that all nodes were visited by DFSing starting from U. This means that we should return true, because this means that there is a path from U to every other node. And otherwise, if there is even one node that still has an entry of false, this means that this node was this means that there isn't a path from U to this node, so we're gonna have to return false. So this is kind of straightforward. For part C, we should provide an algorithm in pseudocode, central node of G, which given a directed graph G returns a central node C. If no such node exists, it returns -1. If there is more than one central node, any such node is considered a valid answer. Your answer should include the running time of your algorithm. Any solution is worth partial credit. For full credit, give an efficient algorithm. The answer of part A should be useful. One naive approach is just applying this algorithm as central of GU that we've defined in part B on all the nodes in the graph. So we can test each node to see if it's central. And the time complexity of this approach would be big O of V times V plus E. This is the time complexity of is central of GU because of the DFS. And since we're applying it on every node, this would be, we would multiply by the size of the set V. The insight to making this approach more efficient, while it is correct, and it would correctly return a central node if one exists and -1 otherwise, to make it more efficient, we kind of have to go back to the definition of a central node and try to derive an insight from there. So we know that if we start DFSing from a central node, all the nodes will be visited at some point. And we know, based on part A, which we've been hinted, and we got this hint to use part A. So based on part A, we know that if we DFS from a certain node, then all nodes that we visit, so for example, let's say we DFS from 2, all nodes we visit, such as 4, or maybe there's 5 here and 6 here. So all nodes we visit, we can conclude that they are not central nodes if 2 is not a central node. So again, we've established that if we start DFSing from U, if U is not central, this would imply that V is, let me move this to the left. If U is not central, this implies that V is not central. So if this is where V is reachable from U. So V is gonna be processed at some point while we're DFSing over U, while we're applying DFS on U. So if we start DFSing from 2 here, and we visit all of these nodes, and then we come to the conclusion that 2 is not a central node, then we can conclude that all of these nodes are not central nodes, right? Because they're reachable from 2, and 2 is not a central node. So the approach we can build is, let's just start DFSing from some node. I'm gonna bring back these nodes because it's a better example that way. So let's start DFSing from some node, and if we reach all nodes, we know it's a central node. This is similar to part B. But if we don't reach all nodes, that's where it becomes more interesting. So I'm gonna also add a node here. Maybe also one here. Okay. So when we don't, when we establish that 2 is not a central node, we're gonna continue DFSing from other nodes. So let's say we start DFSing from 7 now, and once we reach 2, since 2 is marked as already visited, we're not gonna continue DFSing. So once we, so the DFS call on 7 is gonna end pretty quickly, and we're gonna come to the conclusion again that 7 is not central. So we're gonna DFS again from 8. And again, we're going to reach the conclusion that 8 is not central because not all nodes as marked as processed after the DFS call on 8. And then let's say we start DFSing from 0. It's going to visit 1 and 3. And then all the nodes will be marked as processed. And we're left with 0 as a candidate for being a central node. And why is 0 a candidate for being a central node? Because there are 3 types of nodes. There's the last node we call DFS on, which is 0. And there's nodes that we've already processed before, such as 2, 7, 8, etc. So these are the nodes that we had already processed before the last call on 0. And there are nodes that were processed due to the last call on 0. Okay? So there are these three categories of nodes. We know for a fact that in this category, let's say 2, 7, 8, etc., in this category, none of these nodes are central nodes. There's no way they're central nodes, because if they were central nodes, then we would have never DFS'd from 0 in the first place. We would have never made an explicit call to DFS from 0. It would have been part of the recursive calls. So it wouldn't be an initial call to DFS from 0, because it would have been marked as visited, because one of these nodes would have reached it, right? So none of these nodes can be central nodes. Now for these nodes, since they are reachable from 0, then if any of them is a central node, then 0 is necessarily a central node as well. So it's enough to only check 0. If 0 is a central node, then there might be other central nodes here, but we don't care about them. We just want one of them, which is 0. Or we just want one of the central nodes, which is 0. And if 0 is not a central node, then there's no way any of these are central nodes. Because if 0 is not a central node, then all nodes reachable from 0 are also not central nodes. So the idea, to wrap up, is just keep calling DFS as long as there are new nodes to discover or new nodes to process. And once we make the last DFS call, this node that we invoke DFS on at the end is a candidate to being a central node, and it's enough to only check this one node. So to make this more concrete, if we want to define this algorithm, let's call it central node of G. Actually, did they provide a name? Yeah, central node of G. So as you might recall from class, from the implementation of DFS, first of all, we're going to initialize the arrays to be all false. And particularly, we're interested in the in-progress array. So this in-progress array is going to be false. We're going to have V entries that are all false. And then we're going to loop over this. We're going to loop over the edges. Or it's kind of like looping over the entries in the in-progress array. So for u in g.v, actually this should be the size of g.v, we're gonna loop over these nodes. And if the node has not been marked as in progress yet, so it's not processed yet, so if it's equal, let's say, to false, then we call DFS on it. Let's pass in progress to the DFS. And then we want to remember that this is the last node we DFS'd on so far. So let's say last is equal to u. And at the end, we're gonna do something. But for now, let's just make sure this is all clear. So we're just gonna call DFS on all the nodes. We want to visit all nodes. But we're keeping track of what's the last node I've explicitly called DFS on. Because as you know, DFS might do some internal recursive calls, but I care about the last node that I called DFS on. And this last node is basically 0 from this previous example. And as I explained before, it's enough to check if this last node is a central node. So I could just check if is central of G. Okay, so if is central of G last. If last is a central node, obviously we return last. Otherwise, we return -1. So hopefully this all makes sense now. Now let's continue to part D. We say a node S is a sync. Oh, actually, before part D, let's go over the runtime complexity of this algorithm. So here, this is normal DFS. We're only gonna visit each node once. So remember that in this case here, for example, when these nodes were already processed, if I call DFS on 0, once I discover 2, I'm not gonna call DFS on 2 because 2 is already marked as in progress. And you can review the pseudocode for DFS that was covered in class. So this is basically just a normal DFS. So this is O of V plus E. And this is also O of V plus E. So overall, this algorithm is going to be O of V plus E. While recall that the naive algorithm was this times V. So now for part D, we say node S is a sync node if for all nodes V in G, there exists a path from V to S. That is, S is reachable from all nodes. Provide an algorithm in pseudocode sync node of G, which given a directed graph G, returns a sync node S. If no such node exists, it returns -1. If there is more than one sync node, any such node is considered a valid answer. Your answer should include the running time of your algorithm. So what's a sync node? Previously, we've been working with central nodes. Central nodes are nodes that can reach all other nodes. Sync nodes are nodes that all other nodes can reach. So for example, if we have 0 here, and then we have 1, 2, 3, and then maybe we have an H4, then 4. So 1 can reach 0 through this path, 2 can reach 0, 4 can reach 0, 3 can reach 0, obviously 0 can reach itself. So 0 is a sync node in this example. And we want to provide an algorithm that given a graph, it returns any sync node if there is a sync node in the graph, or -1 if there are no sync nodes. Now, obviously, since this is part D of this problem, it might be useful to think about the previous parts. So how can we make use of all the work or all the thought we've put into central nodes and invest it into sync nodes? We could just simply, if we stick to this example, let's say, if I want to find a sync node in this graph, I might imagine reversing all the edges. Since it's a directed graph, so edges have direction. And I reverse all these edges, and now the sync node is a central node in this new graph. So a sync node in a graph, once I reverse all the edges, it becomes a central node. So what I can do is reverse all the edges or flip all the edges in the graph, and then apply central node of G. This process of flipping all edges in a graph, it's called getting the transpose of a graph. So G, and it's kind of a superscript T. This is the transpose of G, which means a graph with the same nodes, but with edges flipped. So an edge UV would if an edge UV was in G dot E, now we would have an edge VU in G transpose dot E. So I'm gonna transpose the graph, and then I'm gonna just search for a central node. So our algorithm would just be this. So it was called sync node of G. and we can simply just find G transpose and return central node of G transpose. And that's it. And to find G transpose, if we assume an adjacency list representation, this would be O of V plus E. And central node is O of V plus E. So overall, this algorithm is O of V plus E. And that's it for the second problem. Now for this third problem, and I think this is like a very important problem, it's called the easiest path. It's from the fall 2023 December 9 final. You are given a directed graph G representing a game. Every node corresponds to a task in the game, and it has an associated difficulty level, which is a positive integer. To play this game, you are given a starting node S and a destination node T. You have a certain proficiency level L, and you need to find a path from S to T. You are guaranteed that there is at least one path. However, you can only pass through nodes whose difficulty level is less than or equal to L, your proficiency level. An example is shown in figure 2. The starting task S has difficulty level 0. Task A has difficulty level 5. Task B has difficulty level 3, and so on. There are several paths one could take to reach T from S. Consider, for example, the path SADT, so this path. To be able to go through this path, you need a proficiency level of 7. In the above graph, the minimum proficiency level you need to reach T from S is 3. So to go through this path, to beat all the levels, we're gonna need a proficiency level of at least 7, because the maximum difficulty is 7. So we're gonna need to match the maximum difficulty and proficiency level so that we can beat all the levels. Given a graph G, starting and destination nodes S and T, provide an algorithm minprof of G, S, and T, explain it and give a pseudocode that finds the minimum proficiency level L needed to be able to successfully complete the game. What is the running time of your algorithm? And we're gonna come back to this follow-up question later. So anyways, looking at this graph, we're not really used to dealing with graphs where the values of the nodes are of concern. So let's move the values to the edges. So what I'm gonna do is, for every edge, I'm gonna assign a weight. The weight is gonna be the maximum between the difficulties at its terminals. So this would have a weight of 5, this would have a weight of 3, this would be 7, 7, 2, 3, 5, 5, 7. You think this is all the edges? Okay. And the reason I'm doing it, I'm assigning the weights this way, is because to beat both levels, so to beat level S and A, you need a proficiency level of at least 5. So to beat both levels, you need a proficiency level of at least the maximum between them. So to move from this node to this node, you're gonna need a proficiency level of 5. And now I can disregard the difficulty levels that are within the nodes themselves, and I can direct my attention to the edges. And now to rephrase the problem, we're asked to find a path from S to T which minimizes the cost. So we want to find the path with the minimum cost, where cost is defined as the maximum edge, the maximum weight of an edge on the path. So the cost of a path is the maximum weight of an edge on the path, and we want to find a path with minimum cost from S to T. Hopefully everything I've done so far makes sense. Now we do know a few algorithms that could help us find a path with minimum cost, but usually cost is defined as the sum of weights on the path. We're not used to dealing with this different definition of cost being the maximum weight of an edge on the path. So let's see if we can modify Dijkstra, which is the algorithm we usually use for positive weights. Let's see if we can modify Dijkstra to account for this new definition of a cost. Let's go over what Dijkstra does again. What Dijkstra does is, first of all, we assign a distance of infinity for all nodes, and then we're gonna, for all nodes except for the source, we're gonna we set the distance of S to be 0, and then we put those nodes in a min heap, and we keep popping from the min heap, and for every node we pop from the min heap, we relax its edges, right? And what does it mean to relax an edge? So what does it mean to relax the edge from U to V having a weight of W? What relaxing is basically we're trying to improve the distance of V, or improve the estimation for the distance of V by using the edge UV. So let's say we have this graph. So we have a source node S, and we have some graph, and then at some point we have a node U and an edge to a node V, and let's say node V is reachable through other nodes as well, or other edges, and the distance so far, so at some point in the algorithm, the distance we've discovered so far for U is let's say 30, and the distance we've discovered for V is 50, and this edge has a weight of 10. So what relaxing is saying basically is, okay, so I can reach, there's some path that takes me from the node S to the node U with a cost of 30, and there's some path that takes me from the node S to the node V with a cost of 50. And now I'm kind of discovering this edge between U and V. So maybe I can use it to improve this 50. Because if I can go from S to U and then go through this edge, and it would cost me less than 50, then that's an improvement over the current path I have. So I'd rather forget about this and just have this path instead for V. So this is what relaxation is basically. And the way we do this is we say X is equal to the distance to U plus the weight of this edge, which is W. And if X is less than dV, then we update dV to be X. Pretty straightforward. And notice that we're dealing with the weights in this way because cost is usually defined as the sum of weights. So the reason why X is equal to du plus W is because if I want to take this path, then its cost would be equal to the cost of this blue path plus this edge, right? But notice that if we change the definition of cost to this definition, then this doesn't necessarily hold anymore. This doesn't necessarily hold anymore. So the new candidate cost is not du plus W. Because if I want to take this red path, then its cost would not be the sum of the cost of this blue path and this edge. It would be the maximum between them. So X would be the maximum between du and W. And again, why is that the case? Because the cost of this candidate path, I'm running out of colors, so okay. So right now we have this candidate path under consideration, which is this red path, right? And they want to check if this red path is an improvement over the current path I have for V, which might be something like this. Or it might have some common nodes. So whatever path I have to V that has a cost of 50. So I want to check if this red path is an improvement. So what's the cost of this red path? The cost of this red path is the maximum, is the maximum weight of an edge along this path. I already know that the maximum weight of an edge along this portion is 30, because that's du. So I just have to account for this extra edge. And to account for it, I don't add it. I just see if it's greater than the maximum, then it's the new cost. Or if it's not greater than the maximum, then the old maximum is the new cost. So basically the cost of this entire red path is the maximum between du and W. Right? And then I just do the same check. If X is less than dV, then dv is set to x. And that's all we have to do to modify Dijkstra so that it fits this new definition of a cost. Now, if we allow for negative difficulty levels, would your answer change? If yes, how? So this is an interesting question. So let's say, for example, this had S had a difficulty level of -1 and A had a difficulty level of -3. Then this edge between them would have a weight of -1. And again, I can just forget about this after setting the weight for the edge. So how would this affect our answer? Would our answer change if we have negative weights? Your instinct might be to say yes, our answer should change, because when we introduce negative weights, usually Dijkstra isn't applicable. And yeah, we have this condition in our mind that to apply Dijkstra, we need all weights of edges to be non-negative. But that's not actually always true, because this condition, we need this condition when we define cost to be the sum of weights. So actually, if you go back to why this condition exists in the first place, when you go over the proof of correctness for Dijkstra, at some point you need the following condition. You need the condition that the cost of a path cannot decrease by adding an edge to it. And notice that so this is the condition we come across if we're trying to prove the correctness of Dijkstra in general for any cost, for any definition of a cost. And notice that this depends on the cost and on the edges. So changing the cost would affect this condition. And in general, when we define the cost to be the sum of weights, then if we have for some path, then to guarantee that adding an edge can never decrease the cost, we would have to guarantee that this edge has a positive weight. So when the cost is defined as the sum of weights, this condition can be stated as all weights must be non-negative. But this isn't the more general form. The more general form I like to think about is this one. So we tend to think a lot about this condition, but this condition is important when the cost is defined as the sum of weights, which is the case we generally deal with. But right now we're dealing with a different definition for cost. So does this do we really need this condition? And the answer is no. Because in this case, with this definition of cost, even with negative weights, the cost of a path cannot decrease by adding an edge to it. Because even if you add an edge with a negative weight, then it wouldn't matter. The maximum would never decrease. If you add a new edge to a path, the maximum would either increase if this new edge has a weight which is greater than the old maximum, or the maximum will stay the same. So there's no way that the cost of a path would decrease by adding an edge to it, and we don't really need this condition because of this definition of a cost function, or this definition of the cost. So it's important to note that changing the definition of a cost might play a role in changing this condition. And this is the more general form of the condition that I like to think about. So to answer this question, no, if we allow for negative difficulty levels, our answer shouldn't change. This ends our session for today. Hopefully you've benefited from these problems, and if you have any questions, feel free to reach out. I wish you luck in all your finals. Good luck.